And rolling.
Okay, so here's the deal, and then we're going to spend today also talking about these trends and oxidizing agents, reducing agents, because it's one of the most vital things that you have to understand. So the first thing you got to figure out and understand is, since it's been 5 days, remember if this reaction is going to take place, what has to be the sign of E naught?
Positive.
Positive, right? Okay.
Wow.
That means the reaction is spontaneous, which means you don't have to dump energy into it. The reaction is just going to take place. Okay. So you have silver and silver plus, and you have zinc and zinc 2 plus. So up there, you've got the values that have been given. Okay. So when you look at this, remember, the more positive a value is, the more likely it is to go in that direction. Okay. The more negative the value is, the more likely it's going to get reversed. So when you look at your reduction chart, okay, where are you going to look? So here's your reduction table, right? Mm-hmm. So you've got, for example, fluoride, K, green, okay, down here you got lithium. So when you look at this reduction chart, where are you going to look to find the best oxidizing agents?
At the top of the list.
Top left or top right?
Top right. Left.
I don't know. So look at this.
Those are your 2 options.
If you're trying to find an oxidizing agent, okay, so if you look at the very top of your list, right?
Okay.
Up there at the top, you have F2 plus 2 electrons turning into 2F minus. That's the very top, right? Halfway through, you've got hydrogen gaining 2 electrons and turning into hydrogen gas, okay? And then down here at the bottom, you have lithium plus 1 electron turning into elemental lithium. That's negative 3.05, and that's 2.87, okay? So if you're to find the best oxidizing agent, are you going to look on the top left or the top right? Or in other words, you're going to look for a reactant, or you're going to look for a product on the reduction chart if you're trying to find an oxidizing agent.
You're gonna look. You're gonna look at that lithium. Right, no. Yeah. No, I don't know.
Okay. If you're trying to find it, what do oxidizing agents do?
Give electrons.
They use
actually
electrons.
reduce. They reduce, actually.
No, reduce.
They
Gain
reduce.
electrons.
Okay, oxidizing agents
Oh.
reduce. Right?
Hello.
So top right.
So if you're trying to find the best oxidizing agent, what are you trying to find? The one that is most likely to give away electrons,
Gain.
or the most likely to gain
Gain.
electrons?
Gain.
Gain electrons.
Okay.
So where are you going to find the best oxidizing agents?
That's.
The
Are you
top
talking about
of
the
the
periodic
list.
table?
No, on this chart,
What
On-
right and left are there?
the products or the reactants.
So
product
here,
side.
here.
Are you going to look on, so for example, are you going to look,
Top left.
You would look on the
are you going to
reactant
look
side.
for fluorine, F2? Are you going to look for fluoride, F minus? Are you going to look for lithium ions or elemental lithium?
Top left.
Top
Left.
Left.
left, because fluoride is going to be very willing to take electrons and turning into fluoride. Okay, fluorine wants to turn into fluoride because it wants to gain electrons, right? It wants to turn into an anion. Okay? So fluorine gas is an extremely effective oxidizing agent, okay? Because of the fact that it's very easily wants to take electrons, right? Now, lithium ions down here at the bottom would be a horrible, horrible, horrible oxidizing agent. Because there's no way, shape, or form does this thing want to gain an electron and turn it into elemental lithium. Okay? It's not what it wants to do. Now, if you were to look for the best reducing agent, okay, where would you find good reducing agents?
Bottom.
Bottom,
Right.
Bottom.
Right.
Right.
bottom right. Because so lithium down here really wants to give up an electron and turn into lithium ions. So lithium as an ion is much more stable than elemental lithium. So this is why if someone says, hey, let's go out to Colorado and we'll go mining for lithium, don't go, okay? You're not going to find elemental lithium because lithium wants to lose that electron and then turn into lithium ion. Same thing with sodium, potassium. Okay? Those elements on the bottom right don't want to exist as in the elemental form. They're much more stable when they give up those electrons. Okay? Now, the elements on the top of the periodic, or the top of this chart, they want to go in that direction. They want to gain electrons so that they become more stable. So the general trend is your nonmetals, fluorine, chlorine, bromine, iodine, all of those. So if you were to look on the periodic table, okay, if you were to look on the periodic table, where would you find the best reducing agents? The metal side or the non-metal side?
Metal side.
Metals.
Metal side, because those want to give up electrons and turn into ions. Now, if you were to look for the best oxidizing agents, oddly enough, then are going to be your nonmetals, fluorine, chlorine, bromine, oxygen, okay? So you have a lot more elements that are going to give up electrons because the vast majority of the periodic table is metals. There's actually, is only as a percentage, there's very few elements that actually are capable of taking in electrons and being reduced and being oxidizing agents. Most of the periodic table wants to give up electrons. There's actually a small portion of it. But thank God we do have that portion that wants to take in electrons, but otherwise we wouldn't be here having this discussion. So that's a good thing. Okay, so with that said, if you look at this first cell where you have silver and zinc, right? Okay? So when you look at your chart, how are you going to figure out which one's going to be the anode and which one's going to be the cathode?
Which one's being oxidized, which one's being released?
So does the reduction happen at the cathode or the anode?
Cathode.
The red cat, right? So here's the question. Which one of these is going to be reduced? Is the silver going to take in an electron and turn into, or the silver ions turning into silver, or is the zinc going to gain 2 electrons and turn into elemental zinc?
The zinc wants to be as an ion.
Yeah. So hold on.
Why is it better? Where are you going? Shadow. Fine.
Okay. We're going to read this. That's just like more of a complete chart. The silver reduction table, and then only do the ones that are circled.
Thank you.
Okay. So, what's going to happen with the silver? The reduction or oxidation? Reduction. So this is going to be my cathode. So the zinc is going to be my, and which direction do the electrons flow?
Anode to cathode.
Anode to the cathode, the electrons are going to be flowing around like this. Okay? So the first thing you want to calculate is your E naught value, which is under standard conditions. Okay? Because if that's wrong, about everything else is going to be wrong. So your answer to number 4 should be like 1.56. Okay?
About.
That sounds
Okay.
familiar.
Because literally, if that's wrong, then all your nearest equations from there on out are going to be wrong. Okay? So, if you look at what's going to happen then on 9 and 10, we're going to calculate this value of E based upon a change in concentration. So, here's, again, how you can visualize this. Okay, there's 2 ways you can think about this, and I don't care. What some people like to do is they think about this in terms of like a party. Okay? So if you look at what's happening on number 9, you've got a small concentration of silver ions. So there's not a lot of silver ions going over there. Hey, come on, let's party, right? And you've got a crowded zinc cell, which makes it harder for those to turn into ions because you've already overloaded. So if you like the idea of, well, okay, I'll think this through in terms of concentrations. Okay, I have a small number of silver ions that are going to be pulling the electrons, and I have a crowded zinc cell. That's going to make it less likely for those electrons to move. So your voltage should go down. Okay? Now, the other way that you can look at it is that you have E equals E naught minus 0.0592 over N times the log of Q. Okay? So in this situation, remember, it's always, this Q value is always products over reactants. And this is why you have to have this balanced equation. So in this situation, it's going to be your zinc ion concentration divided by your silver ion concentration squared. Don't forget to square the silver ion concentration. Okay? That's one of the most vital things that has to happen, because on that balanced equation, there's a 2 in front of that silver ion. So that silver ion concentration has to get squared. So if you look at what's happening on number 9, and if you're a mathematical person, this should speak to you. So what's happening on 9 is that you've got a silver ion concentration, which is 0.01. So you have a very small silver ion concentration. You're dividing that into a large zinc ion concentration. So that means Q is going to be big, okay? It's going to be much, much bigger than 1. If you were actually to find the value of Q, it would be a very, very big number, okay? Now, when you take the log of a number bigger than 1, is that a positive or negative value?
Positive.
Positive. So what's happening is that I've got an E naught value that's always positive minus this times a negative value. So, excuse me, this is going to be a positive value. So since this is a positive value, okay, right, I'm going to subtract this whole thing. So since I subtract this whole thing, I'm going to drop my E naught value. So, excuse me, I'm going to drop my E value. So if you're a math person, if Q is big, E is going to become smaller. So it's like an inverse. Now, the other side of it is, if you look at what's going to happen on number 13, on 13 we've reversed it. Now we have a high concentration of silver ions that are going, yo, come on, let's make the run for the border, right? So you have a very high concentration of those that are willing to pull those electrons, and you've reduced the concentration of your zinc ions. So it's easier for those to go into the solution. So your E is going to go up. Now, the other side of this is that now you have a Q value that's less than 1. So now you're going to take a Q value of less than 1, that makes it negative, so you can have a positive minus a negative. You in effect add it, the E is going to go up. So, I don't care how you think it through, but this is one of the most vital things you have to be able to think through and go, okay, if I decrease the concentration of my anode, if I decrease the concentration of my cathode, what does that do? Okay. Now, let's talk about on that back side on those questions. So, if you look at what's happened on number 6, okay, we're going to add hydrochloric acid. So, to answer number 6, you have to realize that silver chloride is highly insoluble, okay? That's the only way that you can understand this problem, okay? All chlorides are soluble except for silver and lead, all right, and mercury. But we don't deal with mercury much. So being horribly poisonous.
I'm going to eat it.
You could, I don't recommend it.
Not
So,
really
on number 6, what you want to talk about here is because, and again, you have to visualize what's happening. You've got a bunch of silver ions floating around. I'm going to add some chloride ions to it. That's going to form a precipitate. That's going to drop the concentration of my silver ions. Okay? So then, once you drop the concentration of the silver ions, then you want to think through and go, okay, hey, what's that going to do to the cell? Okay?
Mm-hmm.
All right. Anything else you want me to go? Yes?
So that would drop the voltage? Increase the voltage?
Can do one of those two
Make it
things.
neutral?
Okay.
I don't know.
Is
what
that in the
means.
direction of the force normal on a flat table? Or force gravity?
Jason,
Or opposite?
she hasn't had physics.
Pearson.
Yes, and
Those words
just say it
mean
in
nothing
code.
to
Say it in
me.
code.
Okay, Brent,
Yeah.
look, this is a concentration cell, right?
Yes.
Okay, you had a small concentration, and then you had a small concentration, and then you had a big concentration, right?
Yeah.
Okay? Now, so what's going to happen is that we're going to add hydrochloric acid to the concentration cell that's on the left, right? So this is going to make the concentration go down. So at that point, nature is going to flip out even more, because now there's a bigger difference between the two concentrations.
Yeah.
Okay? So with the bigger difference between the concentrations, what's going to happen to the voltage?
Increase. So that
There you go. There you go. Okay? Anything else? Going once? Going twice? So get that handed in. And stop that camera for a second.